Hello, I'm Professor Silviana Amethyst, and I would like to work with you today in our Calculus 1 class together on understanding the formal definition of the limit. Not in a graphical context this time, but in terms of understanding how we would go about proving that a limit is a particular value if we wanted to do such a thing. So I'm going to start by writing down the formal definition of the limit, and then I'd like to talk about how to construct an argument that a particular function has a particular value at its limit at a point. So I'm going to write that definition down now. So I just wrote down a pretty technical string of mathematics, and this right here is the formal definition of the limit. I'll note that it did take about 150 years to come up with this formal definition from the time that Newton and Leibniz were working with calculus. So this definition is the product of much work by many mathematicians across a lot of time. So let's investigate various parts of this statement. So I wrote down the limit statement that we've been using since the beginning of the semester. For example, I could write down that the limit as x approaches pi over 2 of sine of x equals 1. And I wrote that down, and that function does in fact have that limit at that value because the function is continuous. Or as an example, consider the statement, the limit as x approaches 0 of x over x equals 1. Now, this function isn't continuous, and the function isn't even defined at the value 0. So how do I go about proving that that's the value? We've been doing rules in the world of calculus so far for computing limits, and we've shown you how to compute them, but we haven't shown you how to show that they really are them. And this definition that we have on the screen here is the machine that we construct in order to show that a limit actually is a value. So the bottom part of what I have written on the screen, that's the thing that we have to show. We have to show that, and I'll annotate this in, I think, red. So we need to show that for any epsilon greater than 0. That is to say, we need to show that for some epsilon someone else is choosing. Someone else chooses that epsilon greater than 0. It's not up to us. That's someone else's tolerance. And in response to their tolerance, I need to be able to come up with my response. So that's someone else's choice. We need to be able to find a response, our own tolerance, our own window. And that's our delta greater than 0. That's our response. So our response is a delta value. How do we find delta? What needs to be true about delta? The very bottom line is what needs to be true about our delta. This down here needs to be true about our delta. We need every point within delta of A. So there's a tolerance on the x-axis. How far away from A, our point of interest, or x value of interest, how far away from that are we allowed to be? We're allowed to be as far as delta. And if we only go as far as delta A, if we go no further than delta, we are guaranteed that every function value is within epsilon of L. So someone specifies a tolerance on output values. Epsilon is the tolerance on output values. The thing that we have labeled, that absolute value of f of x minus L, that's the amount of error that we're going to accept in function values. We'll accept no more than epsilon. How do we control the amount of error or how far off in terms of function values we are? we control the error by setting the value of delta. So we say if we're only allowed to go as far away from A as delta. That's what this says right here. If we're only allowed to go as far away from A as delta, then we're guaranteed that f of x values are close to L values. How close? Within epsilon. Within epsilon. Maybe this is the first time that you've encountered the word proof in this formal sense. So what it is going to be a string of logic chained together that shows that some condition holds. So the part that's not up to us is that epsilon. So epsilon greater than 0 is given and arbitrary. That part's not up to us. Our mission is to construct a delta in reaction to that epsilon. So what we need to do is do math. And we're going to manipulate absolute value expressions in order to be able to find delta. I'm not going to go through how to do those particular things right now. This is just about the structure of the argument. So our first step is to let epsilon greater than 0 be arbitrary. Second step is to do math and manipulate absolute value structures. The third thing we would do then is to assert the value of delta. So it will generally look like something like 3, let delta equals something. And that something is an expression of epsilon. Usually delta depends on epsilon. And that makes sense because if you want to be within 0.1, you choose some distance delta, and to be within 0.01, you would choose a smaller delta. So if you want to be tighter in function value, you need to be tighter at tolerance in terms of our x's, how far away from A we're allowed to be. So it makes sense that delta should depend on epsilon. And then as our fourth step, we will assume that the absolute value of x minus A is less than delta. And then finally, we will show that the absolute value of f of x minus L is less than epsilon. So that's the structure of the argument that we're going to make. In reaction to some arbitrary epsilon, we will do some math and manipulate some absolute value expressions, where what we're manipulating looks like something of the form f of x minus L. We're gonna try to factor out some constants and do some various stuff. Working with error bounds, stuff's kind of tricky. And that gives us our delta. So then we're going to say to the reader, we're going to say, here's my proposed delta. I found that delta is epsilon over 4. Or delta is epsilon over 10. Or delta is epsilon squared minus something. Whatever you happen to find. Okay, so now I have epsilon greater than 0 arbitrary. I found my delta. Now I need to show that my delta works. And so I will assume that the absolute value of x minus A is less than delta. And finally, we will do basically the steps of step 2 backwards in order to get back to the absolute value of f of x minus L is less than epsilon. So let's show that the limit as x approaches 2 of 3x minus 1 is equal to, quick point where you can check your understanding of limits, what is that value supposed to be? 3x minus 1 is a continuous function, which means I can just plug it in and evaluate. This value should be 5. That's L. Our function f is 3x minus 1. 2 is A. So here's how my argument's going to go. Let epsilon greater than 0 be out of my control. I'm not in control of epsilon. Someone else is. We're doing this process in reaction to someone else's epsilon. Someone down at the Davies Center at UWEC's campus gets to choose epsilon, not me. Step 2. I'm going to work on my absolute value expressions. Number 3. I'm going to propose a delta. Number 4. I'm going to suppose that the absolute value of x minus a is less than delta. But we have a specific a that we're interested in. So it's going to look like the absolute value of x minus 2 is less than delta. Step 5. Show that absolute value of x minus 2 is less than delta implies that the absolute value of 3x minus 1 minus 5 is less than epsilon. So there are a couple of places I want to focus my attention on once again. This is maybe a bit repetitive, but I think it bears repeating. The first thing I'm going to do is surrender control of epsilon. I am constructing delta in reaction to it. And I'm constructing in reaction to any epsilon, not just one particular fixed epsilon, if I'm really doing a full general proof. In Calculus 1 classes, we often will say, here's epsilon as a quarter, find the delta. And we're not actually making you do it for all epsilons, maybe give you a picture or something like that. And that's a specific instance of doing this for one epsilon. For a full proof, you do it for every epsilon. We do some work. I'll do an example of that after I'm done with this little bit of dialogue. I'm going to propose a delta as a result of that work. I'm going to suppose then that I have my distance constraint on my inputs, and then show that I get my distance constraint on my outputs. Let's do this now for this particular problem and actually find the delta for an arbitrary epsilon. I start my proof always by writing proof. First thing I'm going to do, I'm going to let epsilon be greater than 0 and arbitrary. I think understanding the word arbitrary merits its own video. Now I'm going to go over here and do some work on the absolute value of 3x minus 1 minus 5. That's equal to the absolute value of 3x minus 6. And that's like 3 times the absolute value of x minus 2. The x minus 2, oh, that looks like x minus a. So if I suppose that that's less than epsilon, then if I move this 3 to the other side, check this action out. Check this out. I'll divide by 3, and I'll have that absolute value of x minus 2 is less than epsilon over 3. And so now I arrived. So I've got my absolute value of x minus a and a thing on the other side. So that thing on the other side there, that's what I'm going to let be delta. So I'm going to let delta equal epsilon over 3. And oftentimes, people when they're doing these, they'll like do this on a piece of scratch work and hide it. And then they say, where'd you get that delta? You say, insight. You did work to find it. So I find my value of delta, and now I'm going to assume that x is close to a. How close? Within delta. And then I'll show that the distance between f of x and L is small. How small? Epsilon. So I'm going to assume the absolute value of x minus 2 is less than delta. Then the absolute value of x minus 2 is less than epsilon over 3. So absolute value of x minus 2 times 3 is less than epsilon. So absolute value of 3x minus 6 is less than epsilon. Therefore, the absolute value of 3x minus 1 minus 5 is less than epsilon. So the absolute value of f of x minus L is less than epsilon. And then I draw a little box, and that little box there shows that I'm done. So that's the structure of my argument. It was like step 1, epsilon greater than 0 arbitrary. Step 2 often happens on scratch work. Find your delta. 3, propose your delta. 4, assume x is close to a. Number 5, show that that implies that f of x is close to L. That's the basic structure of one of these arguments for using the formal definition of the limit to prove that a limit is an actual value. It's pretty easy for linear functions. That function is linear, and that's very nice. And it makes this basically be like, this is how it's going to go. If you have a linear function, it's like basically going to be like that. If it's squares or something else, the analysis gets a bit trickier. And I didn't want to do one of those in this video because I didn't feel like it'd be enlightening. I wanted to focus on the process, on the assumptions in the steps, so that you might have a greater understanding of how one would actually use the definition of the limit to prove that a particular function at a particular point has limit a particular value. Thank you for engaging with me, and I look forward to seeing you later. Goodbye.